Hi, in this video, we want to take a look at descriptive statistics. All right, so first and foremost, what is a statistic, really? Okay, a statistic for us is going to be a summary of the data. Now, so this is kind of like just a short, brief description of the data that tells us information about the data as a whole. So imagine a situation where I have like 10,000 observations of data. All right, I mean, that's a lot. Now, if I want to fully understand the data, I have to look at each individual data point by itself. Can I do that? No, that's not realistic. I can't do that. I don't have time for it. It's not worth the headache. All right, so what I want to do, I want a quick representation of some feature of the data so that I just, I use that to get an understanding of a whole. I want basically a summary of some feature of the data that I'm interested in. All right, so the ones that we're going to talk about in this video are central tendency and dispersion. All right, so central tendency is the idea of where is the data on the number line. So if I have a number line, like if my dad's like over here, over here, over here, very, very large values, very small values, extremely negative values, and negative and large as, like where is like the middle of my data? Now, the funny thing about this is that when we talk about the middle of data, there's a bunch of different ways to actually define this, depending on depending on what's important to us at the time. The other one we're going to talk about is dispersion. So dispersion is a measurement of how spread out our data is. All right. So the idea is if I know where the middle of my data is and I know how dispersed my data is, I have a good idea of where on the number line my data lives. All right. So let's go ahead and start talking about central tendency. All right. So the big one, the main one that we use in life is the sample mean. That is, so here, the sample mean, here is the formula. I add everything up, and then I divide by the number of observations. I take the average, the sample average, and we denote that with X bar. Okay, so that's a very good one. Now, the middle value is called the sample median, is also a way to get where is the middle of our data. So the middle value, so if I have an odd number of observations, it's just the middle. Now, what if I have an even number of observations? I take the average of the two that are in the middle. Easy peasy lemon squeezy. So when I say, and that's the sample mean of those two. Now, the sample mode is the most frequent observation. All right, so when do we use each of these? So sample mean, in general, if you don't know, that's probably the one you want to use. It has a lot of nice statistical properties that I'm not going to cover in this video. The sample median is a good choice whenever I have a reason to not use the mean. So a time that I would use the median is, let's say I have my numbers are like 1, 5, 6, 8, 2, something like that. And then I have my last number is 10,000. Well, if you think about the math of this equation here, this X bar, what's going to happen is that 10,000 is going to pull the rest, it's going to pull the average away from all the other values. And that situation, because of one number pulling the average away, we feel like it's not a good representation of central tendency. So in that situation, I want to use the sample median instead. The sample mode is the most frequent observed value. Now, this is a good one this is one you want to check frequently to see if you have like a problem in your sampling. So I've encountered data where there was like a minimum value of 0 was frequently came up whenever basically there was measurement error. And so by looking at the sample mode, the most frequent observation, I see it's 0, it's spiking really hard on the histogram, and then all the other values are far away from 0. I was like, hey, what's going on here? These 0 values I need to investigate further. So I usually use the sample mode to check for problems with measurements. All right, so now what we want to do, we want to so when we do statistics, we're not going to be doing pencil button paper. We're just not. We're not going to be using a graphing calculator. It just doesn't have the power we need. We need something with more oomph. All right, so we could use Excel for a lot of things, but where I'm going with this video series is that we're going to be doing things more powerful than what Excel can deliver. So we need something even better. We're going to be using R. All right, so what we're going to do, we're going to generate some pseudo-random numbers. So I'm going to generate 1,000 of them. So my n is 1,000. I'm going to use the sample function to randomly generate numbers 1 through 6. I'm going to have 1,000 of these randomly generated numbers. And then I'm going to do it again over here. And so what I'm doing, I'm simulating that I'm rolling 2 dice. So here are my 2 dice. So when I roll dice, they, we add them up, and that's what we have for a board game. So I'm taking the numbers from a board game. This is the simulation of the first one. This is the simulation of the second one. Now, mathematically, if you want to think about this, think about the first die as being red and the second die as being blue, and that'll help. If you're unsure if this is mathematically correct way to go, this is the right way to go. All right, so now I want to compute the mean of a random simulation of rolling dice. So for that in R, I just use the mean function, and x is the parameter of the vector that I want to have as my numbers. All right. Oh, part of my convention in my personal coding, something that I do, I put a v first whenever it's a vector, and m when it's a data frame or a matrix, a data matrix. I'll put list or L if it's a list object. So I'm always using code when I do my statistics. If you have to use code if you're going to be doing serious computations. What this does for me, the reason why I have this convention is that this tells me what it is that, what is the structure of my object as I work through my code, and it helps me remember how I can handle things later down the road. All right, so we can see that the sample mean is just a little bit above 7. What was that? Does that sound right? I mean, the minimum value is 2, maximum value is 12. The average of 2 and 12 is 7, right? All right, it's 14 divided by 2. So yeah, that looks pretty good. Now notice that's not quite 7. So remember, anytime that I have a sample will never truly perfectly represent the population that you have. That we could sit down, we could use our 7th grade, 6th grade, 7th grade math skills to figure out what is the true average of this, and we figure out the true distribution. It's going to be right at 7. But you can see our sample never perfectly represents the population. It will never. If it perfectly represents the population, there's probably some monkey business going on. All right, so now let's compute the sample median. All right, so here, what I'm going to do, I'm going to use quantile, and I'm going to set the probability to 50%. So I want the point where half the data is less than or equal to this value. And boom, we have 7. All right, that's looking good. Now for the mode, R really doesn't address the mode very well. Professional statisticians don't use it that often, honestly. We use it more for checking data quality than we do as a central tendency, except for when I'm dealing with categorical data. And so here, I'm going to make a table, and I'm going to check the most frequent observation. And so I use the table function, and then I'm just going to go ahead, I save the output as table dice, and then I print the table. And so here are the numbers 2 through 12, and here's how frequently we got them. And we can see our most frequent observation is 7. So for us, 7 is the mode. Now let's take a look. Let's go ahead and take a look at what a bar plot of the table. And so this looks pretty close, not exactly how the true dice rolls would be, but it's pretty close, proportionately at least. Now, the next concept to talk about are sample quantiles. Okay, so a sample quantile, this is kind of a tricky, it's an easier thing to think about than it is to articulate, honestly. All right, sample quantiles are cut points where a percentage of the data is less than or equal to that cutoff. Okay, so if I say the 100% quantile, that is the maximum value because everything is less than or equal to the maximum value. Okay, now the 50% quantile, 50% quantile is the data point where half of the data is less than or equal to that value. Okay, and so I'm going to so I use the notation of Q underscore then with a percentage, and you see the percentage indicates the amount of data that's less than or equal to that cutoff value. Okay, so the ones that are the most important are 25, 55, 25, 50, 75, and 100%. So the and we'll call this the first quartile in a moment, and then second, third, because these are so important. These come up a lot. So we use these three to break up our data into 4 groups. And those 4 groups will be approximately the same size. All right, so these 4 quantiles come up so often that we're going to call them something, they're going to get a special name. We're going to call them quartiles. So quantiles are any quantity, quartiles are fourths. And so here we're going to break up the data into approximately equal groups of fourth. So here Q1 is the 25%. So 25% of the data is less or equal to Q1. Q2 is the 50% mark. So half the data is less or equal to Q2. That is, it's also the median. Q3 is the 75th percentile quantile. And so that is going to be where 75% of the data is less than or equal to that. And then Q4 is going to be the maximum value. Now, something that we also do is we say that Q0 is the minimum value of my data. Now, that contradicts the less than or equal to aspect, but it's a convention. It's all right. Now, if you look at different textbooks, you look at different softwares, quantiles and quartiles will be computed slightly differently. In practice, usually we don't really care too much. We just want something that's close. It can become an issue when you have a smaller data set. Larger data sets is really not an issue. All right, so if I want to get the quantiles, I use the quantile function. And if I want the quartiles, I use the same function also. I just have to specify the proportion of the data I want less than or equal to get each points. So here we can see that 2 is our minimum value. We can see that 25% of our data is less than or equal to 5. 50% of our data is less than or equal to 7. 75% of our data is less than or equal to 9, and 12 is our maximum value. Now, you'll notice also if I omit the probs here, so in my code, you notice I have the probs parameter inside the quantile function. If I repeat this without specifying the probs, you see that I get exactly the same value. These are so important that R just uses these as the default and grabs them because it knows that, or the programmers know that's probably the ones we actually want. All right, so now let's look at sample dispersion. Sample dispersion, I want to know how spread out my data is. Now, a good way to start, a good way to think about this would be maximum value minus the minimum value. That way I can see that entire length between that covers my entire data set. And this is a very good way to start, and it's conceptually easy. The problem with it is that if I have changes, if I were to have changes of my data, something were to happen, the maximum value is just one data point, which means it's vulnerable to any kind of tweaking or changing. We like things to be very stable. The minimum value is just one data point. Since it's just one data point, if things change, it's vulnerable to things going wonky. All right, so the sample range really is not a good choice for measuring dispersion, even though it's the simplest one. The one that's very popular is the interquartile range. Interquartile range, I take the middle 50% of my data. I take the 75% quantile cutoff. I take the 25% quantile cutoff, and then I take the difference. This is going to be this range of values will cover about half of my data. It'll be the middle half. So this is a very good one to use. And really, I'm using all of my data for these computations. Therefore, it's not prone to any problems like the sample ranges. Now, another one that we want to take a look at is the sample variance. And now here, this is an ugly formula, but just work with me. What we're going to do, we're going to take that sample mean, sample average. I'm going to subtract it off of each observation. I'm going to square the difference. Then I'm going to add all those up. So every single value, subtract the average, square it, add those all up, and then I divide similar to an average. Now you'll notice it's n-1. We're not going to worry about why that is right now, but just know that this is a good one to go with. And so this is our sample variance. Why do we like this? Well, there's something called population variance in probability and statistics that we'll get into later that has like a good solid connection like with physics. And because of the background of people coming from physics and mathematics when statistics was first getting developed, they started using that measurement. And that measurement became like the go-to for a lot of things. Also, it has a lot of nice theoretical properties. And so because it has a lot of nice theoretical properties, the sample variance has a lot of nice theoretical properties also. So this is usually the preferred way to go. Now, when do we not want to use this? Well, anytime I have an extremely large value that is far away from the rest of it, called an outlier, rest of my data, I want to use something else. If I have one value that's like extremely large and positive, extremely large and negative, so that my mean is getting pulled away from everything else, or my sample variance is getting pulled away from what the rest of the data says it should be, then I don't want to use this measurement because it's getting pulled away from where I believe it should be. A better choice would be the interquartile range. Now, the next one we want to talk about is the sample standard deviation. All right, so if you look at the sample variance, you notice I have squaring, right? All right, so that means that my unit of measurement is squaring whatever is going on. So if I had feet, let's say I was measuring distance in feet, well, my sample variance unit of measurement would be feet squared. Well, does that really make sense? Does that really click in my head? Is it obvious what that means as I work through stuff? Are we dealing with area now? No, that's, so what we're going to do, we're going to put a square root around our sample variance, and that's going to be our standard deviation. All right, so the standard deviation is it's in the same unit as my measurement. So if I measure in feet, then my standard deviation is going to be in feet. If I measure in tons, then my standard deviation will be in tons. If my measurement is in Fahrenheit, then my standard deviation will be in Fahrenheit. Okay, so the sample variance, honestly, that's better for like theoretical work and proofs and stuff like that. The standard deviation is better for actual real application. I use the standard deviation at work. That's usually the first one I go to. If it's inappropriate because of outliers, I'll go to the interquartile range after that. And I'll only use the range if I have decision makers who have very weak math backgrounds, and they like, if they don't feel comfortable with like sample averages, then I'm just not even going to worry about these guys. Talk about these guys. I'll use range because that's so simple that it's audience friendly when the audience is not comfortable with statistics. All right, so if I want to do the computations, I can use range. Now here you'll notice that R spits out two numbers. It spits out the minimum and maximum value. All right, so in statistics we have two definitions of range. Range, one way, is a measure of dispersion. That's the difference between the max and the min. And then the other definition is the maximum and minimum values together. So here R gives us the maximum and minimum values together. So if I want the range, as I talked about it previously, I do subtraction. Or I can take the difference. The difference function, the DIF, what this does is subtracts values in the vector from each other. Now the interquartile range, very similar, that I take Q1, Q3, and then I take the difference between the two, and boom, we see that it's 4. Now for the variance, the command is just var. For standard deviation, it's SD. And we can see this is the square root of that value, the variance. All right, now empirical distributions. So empirical distributions are an estimate of the probability distribution of the population based off of our sample. All right, so what this does is it takes the data and it looks at what percentage of the data is less than or equal to each possible value. And then it says, hey, let's go ahead and make a mathematical function off of this. And we're going to call this an empirical distribution. And so when we're talking strictly about less than or equal to, it's going to be a cumulative distribution function. In R, I want the empirical cumulative distribution function, and I just pass the data to it, and it'll work it out. So it's kind of, it's not clear what's going on at this point. When I look at the plot, it'll be more obvious. If I pass my empirical distribution function to the summary function, it'll go ahead and give me the summary values. That is the minimum, first quartile, median, third quartile, the max, and it includes the mean also. It throws the mean in with the median. And then, we can get the quartile. All right, so what this is doing is that this is figuring out the values so that where it's figuring out a mathematical function, like in college algebra, of the proportion of the data that is less than or equal to a particular value. So here we can see with 12, we can see that 100% of the data is less than or equal to 12. If I go a little bit to the right, let's say I go over to 13, I see that 100% of the data is less than or equal to 13. That's why this bar is here. Now, if I go over here, if I was to go to, let's say, 1, I can see that 0% of the data is less than or equal to 1. And then if I go, let's say, 2.5, even though that's not a possible value, 2.5, I can see that the same proportion as 2 is less than or equal to 2.5 and 2. So the dots are the actual values we have in our data, and these stair steps are basically extending things because we don't have any observations in between. And that's our empirical distribution function. All right, now the Lorenz curve. A Lorenz curve is a graphical representation of the distribution of data. The curve is a graph showing the proportion of aggregated values held by the bottom percentage of the population. All right, so the horizontal axis corresponds to the proportion of the subjects less than or equal to that point on the axis. The vertical, so the horizontal, the x-axis. The vertical axis, the y-axis, corresponds to the cumulative share of the data. The straight line indicates the line of equality if things were equally distributed throughout, and the curve that we're about to look at is called the Lorenz curve. The bigger the difference between the line of equality and the Lorenz curve, the greater the inequality in the distribution of values. So the big thing to walk away with, the bigger the difference between the line of equality in the Lorenz curve, the bigger the inequality in the distribution of values. All right, so now to get this to go, we actually have to do something first. In my R session, I have to download the package. I have to use install.packages and download this package right here. And now I'll have all those functions to work with. This function is not in base R when you first download it. I'm going to use the LC for Lorenz curve package. I pass the value, and I just tell it to plot it. All right, so this curve, if all those bars are flat from my data, if 2 appeared as frequently as 3, which appeared as frequently as 4, and as equally frequent as 5, then what would happen is that this curve here would be on top of this straight line. Now, another way for things to go is if we had like a lot of 1s, a good number, or sorry, not a lot of 2s, a good number of 3s, a lot of 4s, and then very few of the larger values after that. Then what would happen is this curve would shrink down towards the bottom, then shoot up sharply. So if let's say 900 of my observations were 2, 3, and 4, and the rest were the larger values, with 12 being very, very rare, what would happen is that this darker curve would drop down and then shoot up really sharply far to the right. All right, well, that's all I've got for you. Take care and goodbye.